video number 3, installation, and that's where I am now. So we have a plug there for the milling machine, newly attached. The old blue box is gone, and I now have a... oh, I haven't. I thought I had an empty shelf. It's been encroached upon already. Then behind the door I have a connector for the lathe, so that's just gone on today. See if I can get that out and into shot. So my plans to put 2 wires into one connector have fallen flat due to lack of space in the back of the connector for 2 cables. So that means I'm now going to get some more sockets, because I've got 2 plugs instead of just the one to plug in. And then I've decided, if we pan round to that red and black box, that is electric welder, which can also be connected to 3-phase. So I might re-upgrade that to 3-phase, and that'll mean I'll need a 3rd socket for that one. Now that welder was last powered on 3-phase in 1976, but I had it out a few weeks ago and used it, removing all the wires off the top of it that revealed the plate for instructions for connecting it up to 3-phase. So that's a very good possibility. Right, so what have I got so far? I've got plugs on machines. I've had the milling machine spindle running unintentionally, but that's because that machine is as it is. It's also got a separate motor for the power feeds, and when I tried to operate that, the trip on the generator packed in. Round in this side I've run the lathe, that works off the generator, so it's revolved a little bit, but I'm not running it a great deal as yet. At some stage I'll plan an oil change. It's got a sight glass just there, but no sign of any oil in it. I know there is oil in it, but not really enough, but enough just to see the thing revolves. So I'm now currently, that's good, working on the back of the circuit breakers, the 3 of them there, taking the wire off that terminal and adding it to that terminal, so both the wires go onto that terminal, and then I shall do that terminal into the one under there, and the 3rd terminal into the one behind there. So that is what I am currently working on. The generator is rated 8 amp, and that circuit breaker is rated 9.2 on this label. And I can't hold a camera still, which is no great surprise. But for a generator that will run at 8 amp, a 9 amp trip is absolutely no good whatsoever. For starting of electric motors. So I'm linking out the circuit breaker, so we'll do away with that. Don't want it. Ta-ta. Right, back to the work then. Right, current we want. Right, 2 digits in current. Now when I start this, the milling machine should start. Let's see what current is drawn. See, it's only 3 amps. see what it got up to. And we'll see what we get up to. And we didn't, did we? Nothing at all. Big fat zeros on the ammeter. So my thoughts on this are as follows. If you remember when I was showing the back of the circuit breaker where I was swapping wires over, to the right of the picture there was a white rectangular box thing I kept referring to as making connections behind it. That is a current sensing coil wrapped round one of the wires, I presume for the ammeter. If you've ever heard of a current clamp used by electricians for testing the current flowing through a wire, it is exactly one of those, but permanently set up and connected to a meter. So that current clamp failed to detect any current going through that particular wire, and that particular wire is just attached to one phase. I don't think there's any doubt that what I was doing to the milling machine was putting a significant load onto the generator, as the generator was clearly struggling. So we definitely know there was a load on the generator, and yet there was nothing showing on the ammeter. This, I think, has turned out to be fortunate for me, as it has diagnosed the fault. And that is that one of the phases is not connected to the milling machine, or at least to that motor. The main spindle works on the milling machine, so that motor is getting all three phases, but the one for the rapid traverse is not. I'm pretty sure there's actually no electrical wiring problem, and I'm just guessing that it is most likely to be one of the contactors, or the contact on the contactor or switch that turns that motor on, that's just not making contact. It's corroded, rusted, whatever you want to call it. So for the time being, at least I know what their fault is, that it is an electrical fault and not a mechanical fault like a seized motor. So that in a way is good news, but the bad news about it is I've got to find that fault, or I think I've got to find that fault, and finding the contactor with the fault is the next sort of problem, unless I can sneakily get away with something else. So that something else will appear later, maybe in another video, maybe on the end of this one, as and when I get to recording that event. So for now, this job is on hold until I'm set up for that test, and so we'll say that's it for now on this aspect of the proceedings, and we'll move on to something else. Earlier in this video I mentioned that I was disconnecting the circuit breaker that protects the generator from overloads. You may well be thinking that this is not a good idea, as it is a safety device to protect the generator. Well, I'm not going to leave the generator unprotected. I'm going to add another safety device that will do the job and perform in a better or more appropriate way than a simple circuit breaker. So let's move on to that now. So here's something different. I was having problems getting my milling machine to run, and the electrical load that the generator was providing was more than its normal permitted load. As the generator has a circuit breaker built into it, the excessive load was tripping the circuit breaker very, very quickly. In order to get the generator to provide more power, I disconnected the circuit breaker, or effectively bypassed it. So currently my generator now has no overload protection on it. This I'm not happy with, and neither am I happy with the circuit breaker, as that is a simple electrical overload and will trip out when the overload current is more than the rating of the circuit breaker. The generator is rated 8.8 amps continuous, and the circuit breaker was set to trip at 9.2 amps, which is obviously slightly more than the 8.8, but not very much. As a result, any motor that needed the full 8.8 amps or even 8 amps would draw significantly more current than the 9.2 when it was first started. So technically, while the circuit breaker appears to be correct for the generator, it doesn't permit a brief overload in starting motors. This is something quite common with motors, and most motors will have what they call a starter, which is in view at the moment with a red and green button, sometimes one or two other buttons as well. These starters are simple switches with an optional built-in overload protection circuit. Unlike circuit breakers, the overloads in these starter switches are thermal overloads, and they are based on heat rather than simple electric current. It means that, provided on average the current is below the trip level, higher currents can be drawn through it for short periods of time. This allows for the higher draw currents for starting motors, yet still correctly protects the motor for its full load current. So, having taken out the circuit breaker on the generator, and as the generator is effectively a motor in reverse and has the same overload needs or overload protection needs as a motor, one of these red and green button motor starters is ideal to protect the generator and yet still allow the generator to provide its maximum current for short periods of time. In this video, I'm going to explore this particular starter because I've not wired it up internally as they are designed, and I've done that because I'm not starting a motor, I'm protecting a generator which has its own built-in limitations and doesn't need quite the same protection as a motor would when connected to a main supply which could potentially provide very large currents. My generator cannot do that, and so a little bit of tweaking is permitted, I think. So I shall now whip the cover off and detail what I've done internally to this starter to tweak it to make it suit my purpose rather than the purpose it was designed for. If I start by taking the top off, you'll see that the green and red buttons on the top of the switch operate the green and red push buttons there. We have here the main contactor, so this does all the switching, and if I just move that cover off, that is the actual switch. And you've probably seen, or you may have seen, similar sorts of things in other videos about these devices. This unit is the trip, the overload protection, and one of the things about this particular one, they are actually designed upside down. So if we take the lid off again, upside down, the writing is actually now the right way up. If I zoom down on this, there is this white tab here which slides back and forth to set the current trip value from, on this case, between 7 amps and 10 amps. As my generator is rated 8.8 amps, I've got the mark just fractionally above 8.5. Normally the contactor is not energized, is not switched on until the green button is pressed. The green button has 2 wires going to it which basically feed power to the coil to pull that unit down there. Pulls that down, and that makes contact to turn the motor on. Normally the power to the green button goes through the trip, so that if it trips out, the green button also does not work, so you cannot attempt to restart it while the trip has activated. For the reason that this generator has limited output, I don't need that protection. So I've reconfigured the existing wires. All these wires were in this box when I got it, but I've rearranged them so that the green button will always switch the motor on, irrespective of the trip. But once the green button is released, the trip is in circuit for holding the contactor down, and the motor continues to be switched on. In other words, the green button will override the trip, but in normal use the trip will function as designed. This chart is the overload characteristics for this trip that's installed in this motor starter. I will zoom in a minute on it, but generally we've got 2 curves, one there and one there, labelled. That one's labelled number 1, that one's labelled number 3. There is one that goes from the end of one to part way along the other and dotted and labelled number 2, but we can ignore that one. The number 1 curve is with a cold system, so as if the motor's not been run, and the number 3 curve is for a motor that's been running for a few hours. The trip levels change with time as the trip warms up and the motor warms up, and this is correct operation to take into account the temperature of the motor before a particular load is applied. The trip can be set, and the chart here shows a number 1 for the actual trip setting. Then we can double the value of the trip setting, or multiply by 4 times, 6 times, 7, 8, 9, 10, and we get a different part of the curve that's then applicable. Up the side we have the time. It starts off in seconds up to a minute, and then we go from there in minutes to 40 minutes, and from there in hours up to 2 hours at the top. So if we say we set the trip to 10 amps, then this 1 represents 10 amps as being the full load of the motor. And from that, if we follow that up the timeline, we can see that on a warm motor at 10 amps it would trip at just before 4 minutes. However, most motors are started and stopped, and so we can assume that we're running from a cold motor, and at 10 amps the cold motor curve goes over 2 hours, possibly up to about 4 hours. So at full load this would allow the motor to run for about 4 hours before it tripped. If the motor is running at 0.8 full load, if we follow that line up, it never meets the hot curve, and therefore the motor will run indefinitely at, that would be, as if we say that the 1 is 10 amps, that would be 8 amps. If the motor is further overloaded, say the current is doubled, then it reduces the length of time that the motor will run before the trips. Moving in a bit closer so you can actually read the numbers, we see just the same information. 1 being the current rating, or the setting on the trip. So as I say, if you set it for 10 amps, then at 10 amps it will run for a warm motor to just under 4 minutes. We on there? Yes? No? At 15 amps it would run for 30 seconds, coming across here on that line, 30 seconds. But also at 15 amps a cold motor would run for 2 minutes. So that's how the trip, the higher the current, the shorter the time before it turns the whole thing off to protect it from overheating. And that's the whole purpose of fitting this trip. I've set it to 8.8 or thereabouts amps, which is what the generator is rated for, and so it should run at full load for about 4 hours before it trips out to protect the generator. So I'll let it run at that, and if it ever bothers me, I find it's tripping too early, I'll reset the trip level to something perhaps a little bit higher, and if it's not tripping out, I'll leave it where it is, or maybe even reduce it to just add a bit more protection to the generator. But there we are. That's the chart for the starter push button that I'm going to set up on the generator.